Hello. In this video lecture, I am going to present an example, an R example, where we implement linear discriminant analysis, LDA, and quadratic discriminant analysis on synthetic data, where the number of features is 2, and therefore we can visualize the results to get some intuition how LDA, QDA, and the optimal Bayes classifier behave qualitatively in different scenarios. And then we can retain that intuition. So when we work with more than 2 dimensions, when the number of features is more than 2, and we use that intuition to interpret the quantitative results, because when we have thousands of features, we cannot plot the different regions as we do in this example, as you will see. So these 2 lines just clear the memory and the console. Here I set the seed to 1. Setting the seed makes sure that the randomness, any randomness that is been called upon in this code is reproducible. So if I flip a coin in this code, if I get head, I will always get head. If I throw a die in this code, if I do it once and 2 comes out, the next time I run the code, I will get 2, and you will also get 2. So we can compare our results, and this is great for debugging purposes, because if I wouldn't set the seed to 1, when I repeat the code, then each time when I throw a die, I get a different number. And then I'm calling a couple of libraries that we will be using throughout this code. So the first part of this code is to generate data. We are creating synthetic data, where the number of observations is thousands, and the number of features is 2. This is our feature matrix with n rows and p columns. So each column is a feature, each row is an observation. The total number of classes is 3, so we use capital J. In the book it was capital K, so it's the same thing. PII is the prior probability for each of these classes. So class 1, the probability that the response is 1 is 0.6, 2.3, and 3.1. These are the prior probabilities for Y. Okay, so if you remember, LDA, let me just bring back the book. In LDA, we use the Bayes theorem for classification. We have the probability of the features given the response, and then we have the probability of the response. and then we compute the posterior. So here we have three kinds of responses, 1, 2, 3, and for each of them the distribution of the features will be different. In LDA, we assume that the only thing that is different between the distributions between the features is the mean, but the covariance is the same and the distribution is Gaussian. That is the data generating process underlying, which is assumed in obtaining LDA. And then the rest we covered last week. Now, QDA has a different data generating process. QDA assumes that each of the covariances is different. So the data generating process we use here assumes that the prior covariances are different, C1, C2, and C3, which is the same as sigma 1 in the book. Sigma 1 covariance matrix for QDA and the data generating process for QDA. And this is sigma 2 So you can see that these three covariances, they totally have different forms. So actually I make the correlation negative 0.5. Then the three different means, mu1 and mu2 and mu3 are 0 and 1, 1 and 0, negative 1 and 1. Now, the data generating process. This is the continuation of the lecture where we talk about data generating processes. First, we create a column and fill it with zeros. Then we draw n random variables. Draw n independent random variables from the uniform distribution 0, 1. Okay, so we draw a number between 0 and 1, and then we say, okay, we have 0 we have 0 to pi I 1, then we have pi I 1 to pi I 2, then I have pi I, no, pi I 1 plus then we have this. We go to okay, so we have three intervals, 0 to pi, 1, and then pi 1 to pi 1 plus pi 2, and then pi 1 plus pi 2 to pi 1 plus pi 2 plus pi 3. What is this equal to? What is this equal to? 1. So if our random variable falls between 0 and pi 1, well, then y I equal 1. If it's between these two, then yi equal 2. Then these two, it's 3. So, so we draw a random variable, and if it's in this interval, we assign label 1. If it's in this interval, label 2. If it's in this interval, label 3. And then this way, the probability of getting y1 is pi 1. The probability of getting y2 is pi 2, because the length of this interval is pi 2. And the probability of getting y equal 3 is pi 3, because this interval is the length of it is pi 3. And what we do here is a coding translation of this done to all the rows of y at once. We could have written a for loop, go through the entries one by one, but this is more efficient, and whenever we can, we want to avoid writing for loops. Okay. So let's just run this a little bit. Okay. So C1 has this correlation matrix, C2 has this correlation matrix, and C3 is this. Then we create. So now y is filled with zeros. Then for each of entry of y, we draw a random variable between 0 and 1. So unit. These are all numbers between 0 and 1. And now actually if we draw the histogram, you can see that the distribution is uniform. Almost uniform. Obviously these are perturbations, but if I do this, then it looks more uniform. Yeah. Between 0 and 1. Okay. Then we're going to say, okay, find me those observations for which the label should be 1. So we run this. So class 1 ID is a list of trues and falses So the last three entries are, it says true, meaning that the last three entries of uniform are less than pi I1. So this is 0.6. The last three entries of uniform, these three are less than that. But this one is larger. This one is larger. Anyway, this is just to illustrate how we find the entries for which the label should be 1, and then we say, okay, set those to 1. And then we find those that should be 2, set those to 2, and then in the end we just turn it into a factor so R doesn't get confused whether it's dealing with a regression problem or a classification problem. We don't want to confuse R. And it tells us, when it's a factor, at the end it tells us the categories it can take, 1, 2, 3. This is a data generating process, part of this lecture. Now, what is remaining, there's just one piece still remaining for the data generating, and that's generating the features. And for that, what we are going to do is we are going to all the responses, like one by one. We look at the first one. Okay, it's 1. If it's 1, then we will fill the row of x, the corresponding row of x, with a multivariate Gaussian random vector with mean mu and covariance c, but c is going to be c1, because if yi is equal to 1, this entry will be true, and this will be false, and this will be false, and then these two will be 0, so we'll have true times c1, which essentially just selects c1. The same thing for mu1. So, yeah. So, the data generating process for QDA is the mean and the covariance will depend on the label of that observation. Okay, so let's look at X. X has many rows, 2 columns, and let's plot the scatter, or plot x1 against x2. Oh, sorry. All the rows, first column, all the rows, second column. So you can see that there are different clouds. There's one here, there's one here, there's one here. I mean, we have to color code it to see what's really going on. So let me also just do some color coding. How do we do color coding? I don't know. Okay, I guess there's a color, and I put it as numeric y. Let's see. Wow. Okay, cool. So this is one cloud, this is the second cloud, and this is the third cloud. You see they have different orientation, different centers. This is around here. So let's see which one is mu1. Mu1 is 0 and 1. So this should be 0, this should be 1. 0 and 1. So okay, the black one is the first class. Black is the first class. Another way of seeing that is also that the correlation is positive. It's in this direction, as you can see. It's positive. So x2 and x1 have a positive correlation. Now, when it comes to mu2, it's 1 and 0, and 1 and 0. So it's this one. The center is here. You see the orientation is in this direction, meaning that the correlation should be negative. The off diagonal should be negative. Which it is. Okay. And then the third category should be, I think mu3 should be 1 and negative 1, or the other way around. Mu3, negative 1, and the C3 is positive. Okay, so this is how we generate data. Okay, so next thing we want to try the optimal Bayes classifier and QDA. So what we do is, let's look at this. You see, this is the scatter of our data of the features. So x1, the first feature, the smallest amount is somewhere around here, negative 2.5 to somewhere plus 2.5, and x2, the second feature, starts from somewhere close to negative 2 to positive 2.5. So what I will do, I will take this surface and I break it into a grid and I create points. So what I want to do is I want to color code these different regions according to what the classifiers say. And to do that, I have to break this into a grid and then see what the prediction for each point on this grid will be, and then I will plot it. Okay, so this line of code Okay, this line of code, these two, it creates a feature matrix where the number of rows is the number of points in the grid and the number of columns is 2. And what it does is it makes sure that the first entry starts from the minimum of the first feature to the maximum of the second feature, and it breaks it into 100 points. And then the second will be from the minimum second to the maximum second, also 100. So in total, this will lead to 100 times 100, which will be 10,000 rows. 10,000 rows, 2 columns. And now for each of these rows, we have a predicted label based on the base classifier. Well, for now we fill it with zeros, and then we have one for the predicted label using QDA. Okay. Now, to come up with the parameters needed for QDA, we estimate the probabilities involved in the data generating process from the data. So instead of using the true mean and covariances, which the oracle only has access to and the base classifier has access to, we will estimate them from the data. Okay, how do we estimate the prior probabilities for the label being 1? Well, we just count how many we have and then we divide by the total. We do that for the second category, we do that for the third category, and we fill it in a vector calling pi hat. So pi was 0.3, 0.6, 0.3, 0.1. Pi hat, my guess is because we have 1,000 observations, will be very close to these three numbers. But you see, it's not exactly the same, because even though 1,000 observation is large compared to 2 features, it is still not infinity, and that will create some variability. Then what we will do is we will separate the features for which the label is 1, 2, and 3 and put them into 3 different matrices. So we essentially say only the rows for which the corresponding label is 1. Pick those, put them into x1. Only the rows for which the corresponding label is 2. Pick them and put them into x2. So once we have separated the features, we calculate the sample mean within each category and the sample covariances within each category. So we have Again, because the number of observations is large, these estimates will be true to the will be close to the true ones. So, for example, mu1 versus mu1 hat, very close. Mu2 versus mu2 hat. Now you can play, reduce the number of observations, and you will see this discrepancy will increase. It will become more random and it will decrease. Now C1 versus C1 hat. Very close. Okay. We need or discriminant function. Okay, here's an error I have recognized. Has anybody recognized an error here? This sigma should be sigma k. Anyway, we have to calculate this quantity for 1, 2, and 3, and whichever is largest, that will be the assigned label of this observation. So what I'm doing here, this line here, is nothing but these two lines where there's a k here, and we are doing it for k equal 1 here. Then we will do it for k equal 2, and then k equal 3, and you spend some time on this line, you will figure out how is this related to this. I can tell you a few things that might be helpful. First of all, here we have a transpose, and that T here transposes whatever is inside. This is mu1 minus the transpose of x grid I. So this is the ith row of the x grid, and because it's a row, we have to transpose it, so it becomes a column vector, and then we subtract mu1 from it to get this part. And then we transpose it, and then we have the negative 0.5, and then we have negative 0.5 log determinant of this. Right? And then we have log of pi k, which is this. And here we have sigma k inverse x minus mu k. This is solve C1 essentially does the inverse, and if you're doing matrix vector multiplication, you use the percentage star percentage, and yeah, that's it. Okay, then so we are going over every row of X grid because we want to know what is the discriminant function for each point on this grid, and whichever is bigger, that will be the corresponding label. And here we are using the true values, therefore this is the Bayes classifier. Here we are using the estimated values, therefore we get the QDA. Now, once we have the predicted um, classes for each point on the grid, both for the Bayes classifier and for quadratic discriminant analysis, the next thing we need to do is to plot it. That's why we create these data frames, and I mean the rest has nothing to do with machine learning. It's just basic data visualization, so I don't spend time on it, but you can just easily Google. It's mostly everything is from the ggplot library. So let's just plot it. So Bayes classifier, QDA, very similar. This should not be y, this should be x2, x1, x2, x1. This is wrong, this should not be y. You can correct it. Now if I reduce the number of data points, the difference between the Bayes classifier and QDA will become more pronounced. So let's have 100 data points. Okay, you see there's a bigger difference now between QDA and the Bayes classifier. Now let's do this with 20 points. So 30. Now we have these few data points in each class, and the Bayes classifier has access to the true parameters, so that's its boundaries, but the QDA is just has less data, so you see there's a bigger difference. Okay, that's this part of this lecture. Coding, synthetic data, QDA, Bayes classifier, how sample size changes performance, and the decision boundaries.